All right, so this is going to be our introductory portion to topic 6.3, where you are learning how to do stoichiometry. All right, so we will quickly define what stoichiometry is and why it's useful in the world of chemistry, and then we'll go over how an example of how you will use stoichiometry to calculate things. All right, so stoichiometry is a calculation method, right? So just like we've been doing all year long in chemistry, lots of mathematical application. This is your algebra-based science requirement, by the way. So stoichiometry is a calculation of a theoretical yield. So in other words, how much product, right? Or how much reactant do we need? So how much product will we get? How much reactant do we need? We can use stoichiometry for all those types of applications, right? Now, these types of calculations, these are fundamental in the world of chemistry, right? So chemistry, is intrinsically valuable because it allows us to helps us to understand the world, the way things operate, why certain things combine with other things, right? Intrinsically valuable, but it's also exceptionally valuable in terms of how we can use chemistry to better our lives, to create new materials, to create new medications, and so on, right? Now, we've done a lot of looking at what combines with what, right, and in what ratio and so on, okay? Now, when we conduct a reaction, though, where this reacts with that, right, we've learned about how to balance those reactions. What we need to be able to do, though, is take a given quantity or identify what quantity we might need, right, so that we can create a certain amount, and in some cases, a very precise or exact amount of the product. Right? So in the world of medications and pharmaceuticals, super important to be able to make those calculations and get them in. In the world of mining, if we're going to try to extract a valuable metal from a mineral resource, right? We want to know how much of a certain reactant we might need to be able to extract that or precipitate it out of a reaction. Okay. Now, making a popular reference, if you've read the book or seen the movie The Martian, right? There is a part of the book where he is trying to create water on Mars using hydrogen and oxygen and a variety of things. He gets his stoichiometry wrong and ends up causing a bit of an explosion. All right. So you need to revisit his high school chemistry to get that right. Anyways. So stoichiometry allows us to calculate how much product we ought to get, how much reactant we might need to get a desired amount of product. Okay, and we're going to go through the steps of how that works. All right. So in the case of a common reaction, the combustion of propane, right? So you guys have probably seen and used propane quite often in your lifetime, right? So propane is C3H8. That's our hydrocarbon, right? Whenever we burn something, typically we have to add a little spark to get that reaction to go, right? That means it's reacting with oxygen, and in the case of burning something like propane, we're going to produce carbon dioxide and water vapor as a result, as long as there's plenty of oxygen. Okay? Now, we have learned that we need to add in coefficients, like this 5, this 3, and 4, to make sure that the reactants, the amount of atoms, the total numbers of everything on the reactant side is equal to the total number of everything on the product side. Okay? So when we add those coefficients in, we get the same amount of things on both sides. But in the world of stoichiometry, one of the things we want to think about it as is a ratio. Okay? So in the case of the combustion of propane here, all right, the ratio that we're talking about is we have essentially 1 mole of propane, right? In order to completely burn up or combust 1 mole of propane, we need 5 moles of oxygen gas. to get that to go. All right, so we need a 5-to-1 ratio. Now, we could always have excess oxygen gas present, okay, but to completely combust 1 mole of propane, we need a minimum of 5 moles of oxygen gas. Okay, if we had more than 5 moles, that just means there'd be some oxygen left over. If we had less than 5 moles, that means we wouldn't use up the entire mole of propane. Okay, now, if we use up all 5 moles of oxygen and all of the propane, 1 mole of propane, what we'll produce is 3 moles of carbon dioxide and 4 moles of water vapor. Okay, now, once we have this balanced equation, right, you'll notice that the units we're using here is allowing us to identify a ratio. For every X amount of propane, I'm going to have 5 times that much oxygen gas to burn it up in terms of moles. Okay? Now, let's look at this in terms of calculation. So basically, I want you guys to work on remembering these 4 steps right here. All right? And this being a video, I'm not going to sit here and wait for you to copy these down. You will just simply hit pause and write them down. Okay? So make sure you get this in your notes. Right? And you can use them as you learn to practice this, but of course we do want to get to the point where you don't need those 4 steps in front of you to successfully navigate this. But for the beginning of this, it should be fine. So hit pause, write these 4 steps down, and then we'll go through an example on the next slide. All right. So we'll do one example in this little set of notes, and this will accompany entry tasks and stuff like that. We'll do some more examples, and of course you'll get to practice these in ChemQuests and other formats. Do a lab or 2 where we use stoichiometry to make predictions and so on. All right? Anyways, in this case, right, we are starting with 59.4 grams of propane gas. Right? Now, we are in grams here, right? So first thing we should note is we're going to need to, in order to associate this amount right here, the 59.4 grams with this reaction, we're going to have to convert the known quantity to moles. So you guys will notice step 1 is already done for you. Nice, Mr. Huderberg wrote a balanced reaction for you already. All right? Now, the amount of propane we are referred to in the question is not in moles yet, so I'm going to have to convert it to moles. And you guys have already learned how to do that back in topic 6.1, right? So to go from grams to moles, I just divide by molar mass. All right? Now, again, if you don't remember what molar mass means, shame on you, but go back to topic 6.1 and look up that information. All right? But, so step 2 here, I'm going to convert my given quantity to moles. So in this case, I have 59.4 grams of propane. Okay? Now, to convert to moles, I'm going to have to divide by the molar mass. I'm going to go divided by, right, molar mass of propane, so 3 carbons plus 8 hydrogens is 44.11 grams per 1 mole. All right, now we're dividing by a like unit, so grams divided by grams cancels that, so we're going to end up with our answer in moles. When we do that and round, we have 3 sig figs here, so I'm going to round this to 1.35 moles of propane. All right, so we just did step 2. Check. Okay, now we're trying to predict the grams of CO2 that are produced in this reaction. So we're making one important assumption here that might become important later on, but the assumption is we have excess or plenty of the oxygen. So we're not going to worry about how much oxygen we have. We're just going to assume we have plenty of oxygen to react all that propane. So all we're going to do is compare our propane amount and use that to calculate the amount of CO2. All right, so the next step here is we're going to multiply by our mole ratio. I'm going to show you what that looks like, right? So we know we have 1.35 moles of propane. So step 2, step 3, I'm going to take my 1.35 moles of propane, okay, and I'm going to multiply that by a ratio. And in calculations, we set up ratios like fractions, okay? So whatever unit, right, or whatever substance we have here in this step is going to go on the bottom, right? So the number of moles of, that's horrible writing. All right. So again, the number of moles that we're starting with, which would be moles of propane, right? We're always going to take whatever the mole ratio associated with that is. That's going to go on the bottom of our fraction. All right, and whatever we're trying to calculate for in the reaction is going to go on top. So in this case, I know I have 1.345 moles of propane because I just did that calculation, right? So whatever I know I have goes on bottom. So moles of C3H8 here. We're going to go moles C3H8 on the bottom. The top is whatever we're trying to figure out. So in this case, it would be moles of carbon dioxide because that is what we're looking at. So I'm going to go moles CO2 on top. Now, all I'm going to do is write in the coefficients. CO2 has a 3 next to it. So I'm going to go 3 there. Propane is just 1 mole, so 1. All right? So what I do in my calculator at this point, okay, I'm going to multiply 1.35 times 3 and then divide, in this case it's by 1, okay? So it's sort of a redundant step there. But if this were a 2, for example, I would go 1.35 times 3 and then divide it by 2. So that is our mole ratio, 3 moles of CO2 for every 1 mole of propane, right? Knowing what goes on top, right, is whatever you're trying to find. Whatever's on the bottom is what you already know, all right? So that helps you identify what to multiply by and what to divide by, right? So we're going to multiply 1.35 times 3, okay, and then just go ahead and divide by 1 just so we get used to doing that step if it's necessary. And we should get 4.05 moles of CO2. Okay, now, final step here is it says to, so step 4, it's going to come up, it says to convert to our desired unit. And in this case, our desired unit is grams, right? So, again, we know the number of moles of carbon dioxide. I want to know the number of grams of carbon dioxide. And again, you've already been taught that. So for step 4, I'm going to go, instead of going from grams to moles, I'm going to go from moles back to grams in this case, right? Which means I'm going to, instead of divide by the molar mass, I'm going to multiply molar mass, right? But I'm going to use the molar mass of carbon dioxide this time, not the molar mass of propane. And oddly enough, they happen to be pretty darn similar, all right? So this would look like, final step here, I'm going to go 4.05 moles of CO2 times, right, because in this case I'm going from moles to grams, which means I multiply the molar mass of CO2, so 1 carbon plus 2 oxygens is 44.01 grams per mole, right? We're dividing by like a unit there, right? And then if I go 4.05 times 44.01, I should get 178 grams CO2, right? I didn't add any of the decimals because I am limited to 3 sig figs. So 178 has all 3. And we are done, all right? Adios.